Hello, my name is William Thompson, and I'll be presenting our work Efficient and Compact Convolutional Neural Network Architectures for Non-temporal Real-Time Fire Detection. For context, here is some snapshots of our visual fire detection system in action. You can see that the two images on the left are showing our binary classification system, green border being no fire and red being fire. However, on the right is the localization output, with the green sections defining areas of fire and red meaning no fire. When a fire breaks out, we want mechanisms to quickly identify and locate the location of the fire. Traditionally, the mechanisms used are smoke and heat detection. However, in some situations, such as open areas, only once the fire is of a substantial size, it will be detected. Therefore, it is critical we explore and evaluate different visual fire detection mechanisms to complement traditional fire detection sensor systems as a source of initial detection. With the ongoing consideration of remote vehicles for automatic fire detection and monitoring tasks, it is crucial that if we are going to have visual detection computed on board, that it is done fast and efficiently. In this work, we are investigating recent advancements in efficient, high-performing convolutional neural network architectures and their variants for the non-temporal real-time bounds detection of fire pixel regions in video and still imagery. There have been a lot of recent advancements in this field, with architectures being optimized for devices such as mobile phones that have not been applied to the task of visual fire detection. Detecting fire in images and video is a challenging task among other object classification tasks due to the inconsistency in its shape or pattern and that it varies with the underlying material composition. We decided to use an end-to-end architecture, feeding raw pixel values as input into the machine learning model. We are using deep CNN architectures due to their ability to capture complex patterns and relationships that are hard to define. There have been recent works adopting this end-to-end approach for non-temporal fire detection. The works outperform the conventional architectures by simplifying a complex, high-performance, generalized architecture. The FireNet and Inception v1 on fire are proposed in the works by Dunnings and Brecken, where the architectures are simplified versions of AlexNet and Inception v1. Further architectural advancements were then explored. Inception v3 and v4 architectures are experimentally simplified in the most recent work, achieving an accuracy of 96% for full frame and 94% for superpixel classification task. Both achieve a high accuracy while maintaining a high computational efficiency and throughput. Two architectures we chose to explore are ShuffleNet v2 and NASNet-A mobile. We chose these architectures due to their compactness and high performance on the ImageNet classification task. Both architectures have high-level structures, containing a composition of defined normal and reduction cells. The fundamental difference between these two architectures is how the cells are structured at a low level. Due to the modular structure of these architectures, it is easy to remove and modify the different cells. The normal cells maintain the same dimensions as the input, allowing for deeper architectures without a reduction in the dimensions. These contain point-wise convolutions and depth-wise convolutions that allow the network to go very deep without the number of parameters blowing up. The reduction cells are the components used to gradually reduce the dimensions down, up to the point of the binary output of fire, no fire. We start by training the reference architectures on the full-frame input, optimizing for binary output of fire, no fire. We then experimentally investigate variations in architectural configurations of each reference architecture by removing different normal and reduction cells and assess the performance on the binary classification task. We then apply a filter pruning algorithm to remove the least important filters, hence reducing the number of parameters further. In the simplified CNN architectures, we use transfer learning from network models training on ImageNet by removing the final fully connected layer from both architectures and create a new linear layer that is mapped to a single value. We freeze most of the components' parameters to prevent the network overfitting during the training and allowing us to train the model longer for better generalization. Once we have defined our simplified architecture variants, we take them and apply them to the localization task. We feed the model superpixel segments created by the SLIC algorithm. The model then classifies each segment as fire, no fire. These segments then build up the image, outlining where the fire is contained in the image. The filter pruning algorithm works by fine-tuning the model, analysing the model's filter outputs to find the influence each filter has on the result. We sort and remove the least important filters from the layers, then retrain the model. If the model still performs with a high accuracy, we further prune the filters and start again until the performance of the model starts declining. This allows us to maintain the same layers of the architecture while removing a large number of the parameters. With exhaustive experimentation using both architectures, we propose the following two reduced complexity architectural variants, modified for the binary classification task. The graphs on the right show the different architecture variants and their overall accuracy after training. NASNet A on Fire is a variant that contains only 2 normal cells compared to the previous 4 in between the reduction cells. The normal and reduction cell lower level architecture remains the same. The total number of parameters in NASNet A on Fire is 3.2 million. ShuffleNet V2 on Fire is a variant with the same fundamental architectural design as ShuffleNet V2. In ShuffleNet V2 on Fire, by applying the filter pruning strategy, we reduce the number of filters in the final convolutional layer, which leads to a total number of parameters being only 155,617. The final convolutional layer initially had nearly 200,000 parameters. After pruning, this layer contained only 12,288 parameters, while increasing the accuracy. Looking at our results of the simplified architectures compared to the state-of-the-art for binary classification, using the same test datasets, we can see we achieve a low false positive rate of 0.03 for NASNet A on Fire and 0.05 for ShuffleNet V2 on Fire, while maintaining a comparable performance of 0.95 for overall accuracy. In the table below, ShuffleNet V2 on Fire improves on the computational efficiency by 7.8 times, achieving 608.97, compared to the Inception V1 on Fire. It is also improving on classification speed compared to FireNet, while having 437 times fewer number of parameters. We also measure the runtime of our proposed architectures on low-powered embedded device, the NVIDIA Xavier NX, achieving speeds of 35 frames per second and 49 frames per second via TensorRT using FP16 operation. For superpixel-based fire detection, NASNet A on Fire achieves the highest true positive rate with 0.98, outperforming the prior works. Both architectures have a high overall accuracy of 0.97 and 0.94 for ShuffleNet V2 on Fire. The table below presents the computational efficiency of superpixel localization running on a GPU configuration. ShuffleNet V2 on Fire provides the maximal throughput of 18 frames per second and is the most computationally efficient when compared to prior works. Some of the examples on the right present challenging scenarios that could lead to false positive detection. These examples demonstrate the robustness of the proposed architecture for the fire detection task in various challenging scenarios. You can see we have an image containing a fireman wearing an outfit similar colour to the fire and an image containing a red colour truck. We will now show a demo of the model working on test data. Overall, we have proposed a reduced complexity CNN architecture that is over 6 times more compact and over 2 times faster than the prior works for fire detection, with a size of roughly 0.15 million parameters. NASNet A on Fire and ShuffleNet V2 on Fire also achieve similar performance accuracy, with 95% for full frame and 94.4% for superpixel-based fire detection. Subsequently, implementation on low-power devices, achieving 49 frames per second, makes our architecture suitable for various real-world applications. Thank you for listening to this talk. Does anyone have any questions?